Okay, in this lecture we're going to finish our section 2.2 material on determining volumes by slicing. And in the last part of this section we were talking about finding the volumes of solids of revolution, which are solids that are generated by taking some region in the plane and revolving it about a line. And we had seen in the last part of this section a method known as the disk method for determining a volume of a solid of revolution. Now, not every solid of revolution can be, or we can't find the volume of every solid of revolution using the disk method. So the method that we're going to talk about next is known as the washer method, and it's somewhat similar to the disk method, but a little more complex. So let's consider our problem of interest for this lecture. Suppose that we have two functions f and g which are continuous, and f of x is greater than or equal to g of x, which is non-negative on some interval from a to b. So let us suppose that we want to find the volume of the solid S, which would be obtained by revolving this region R between the curves y equals f of x and y equals g of x on the interval from a to b about the x-axis. So let's get a visual of the problem that we're trying to solve here. So we were told that we have the graphs of two functions, y equals f of x, shown here, and y equals g of x. So these are both non-negative functions. And as in the statement of the problem, we were supposing that f of x was greater than or equal to g of x. So the graph of f of x lies above g of x. And we're looking at the area of the region between these two functions, or between these two curves, on the interval from x equals a to x equals b. So we have this solid region, and we're supposed to take this region and revolve it about the x-axis. So when we do that, we see that we would get a solid S whose outer edge looks something like this, and our inner edge looks something like the following. And we can see, because this region between the two curves did not come in contact with the x-axis, that there's some hole that is going through the center of our solid. So it's sort of hollowed out through the middle. So in general, looks something like this. So we want to find the volume of this solid that we're calling S, which is clearly a solid of revolution. So one way that we can think about doing this is similar to what we did for the disk method. Let's think about taking a small slice through the region bounded between these two curves at a point x, somewhere along the x-axis between a and b, and let's call the width of that thin slice dx. Now, if we consider just that slice and we revolve that slice about the x-axis, we see that it would trace out this washer shape. So here we don't have a solid disk because our slice here, shown in red, was not coming into contact with the x-axis. So we have a washer-shaped slice. That is like a disk with a hole through it. So our goal is to first find the volume of this little washer-shaped slice, and it's a cylinder shape, really, where the base of our cylinder is some like kind of a donut shape. It's called an annulus, and the area of that base of this cylinder would be found by taking pi times the outer radius of our washer which would be the distance from the x-axis up to my outer curve, which was given by f of x. So we're going to take pi times the outer radius of our washer, which would be given by f of x squared. And then we would subtract the area of the inner circle. That is the part of our washer which is hollow, which would be given by pi times the inner radius of our washer squared. Now our inner radius would be the distance from the x-axis up to the bottom curve, which was given by y equals g of x. So we would have pi times the inner radius, g of x squared, or factoring out a pi from each term, we have pi times f of x squared minus g of x squared. So this is the area of that little cross-section of my washer. But if we're interested in volume, well, we would take that area of our cross-section and then multiply by the thickness of this little slab that we're taking, which we said was equal to dx. So the volume of this little slice, I'm going to call a differential of the total volume of the solid that I'm looking for. And it would be defined as the area. Let me maybe move this down so I've got a little more room to write this out. So the differential of volume would be the area that we just found, pi, times the difference in f of x squared minus g of x squared, times the thickness of our slice, which is what we were calling dx. So then to find the total volume of our solid, well, I want to add up the volume of all of these little washer-shaped slices from the value x equals a from the left edge of my solid up to x equals b, the right edge of my solid. And this process of adding up the volumes of these little infinitesimal washer-shaped slices would be given by a definite integral of this function for volume that we found. So this result is known as the washer method, and it says, making this more formal, suppose that R is the region between the curves y equals f of x and y equals g of x on an interval from a to b. So if the region R is revolved about the x-axis, then the volume of the resulting solid is given by the integral of this differential for volume that we just found. So our volume would be the integral of pi times the outer radius of our washer, which was given by f of x squared, minus the inner radius of our washer, which was given by g of x squared. And of course, that constant pi I can bring out in front. And we're integrating here from a to b, where a and b are the limits of our solid along the x-axis. So let's see if we can work through some examples making use of the washer method to see how it differs from the disk method and become a little more familiar with how this works. So in our next example, we're told to find the volume of the solid obtained by revolving the region bounded by the curves y equals x squared and y equals 2x about the x-axis. So my first step in this problem, much like we were doing for the method of cross-sections or the disk method, would be to sketch my region of interest. Usually helps to sketch your region, to visualize what method you're going to use and determine your limits of integration. So in order to determine what my region looks like, well, it's the region bounded by these two curves. So I need to know where they intersect one another. So to find my points of intersection, I'm going to set these two curves equal to one another. That is, x squared will be equal to 2x. And it follows that x squared minus 2x is equal to 0. Or if I factor out an x, I'm left with an x minus 2 is 0. So x is equal to 0 or 2. So I have the x coordinates for my points of intersection are at 0 and 2. Now let's find the corresponding y values. So when x is 0, y, which is x squared, would also be 0. So both curves have to pass through the origin. And when x is 2, y, which is x squared, or 2 times x, is equal to 4. So they also pass through this point 2, 4. Now let's think about what these curves look like. So my first curve is y equals x squared, which is a parabola opening upward, passing through these points. So a rough sketch looks something like this. And my upper curve is, the other curve, which happens to be my upper curve, is y equals 2x, which would be the straight line connecting these 2 points. So that is the line of slope 2 passing through the origin. So my region of interest would be this shaded region bounded by those curves. Now I'm supposed to take that region and revolve about the x-axis. So the first thing I need to determine is what method I'm going to use here. So let us think about if we were to take a slice through this region at a point x along the x-axis between 0 and 2 of a thin width dx. Now I can see if I revolve that slice about the x-axis, I would get a washer instead of a disk. Now why not a disk? Well, the edge of my region doesn't come in contact with the x-axis, so it's going to have some hollowed out portion through the middle. It's not a solid disk, but a washer. So using the washer method, the volume of my solid would be given by pi times the integral along the x-axis from x equals 0 was our first point of intersection, and x equals 2 gave this second point of intersection. So here we would integrate from 0 to 2, and the function that we're integrating would be found by taking the outer radius of our washer squared. So let's think about our outer radius, which would be the distance from the x-axis up to the larger curve, which was the curve y equals 2x, or our line. So the outer radius of our washer was given by 2x. We square that radius. And then we're subtracting the inner radius of our washer, which would be given by the distance from the x-axis up to the lower curve, which had the equation y equals x squared. So the inner radius of this washer will be x squared. We're squaring that radius. And then the thickness of this little slab was dx. So here we're adding up the volume of all of these little washer-shaped cross-sections from x equals 0 to 2, and that will give us the volume of our solid we're interested in. So here, simplifying our integrand, we have pi times the integral from 0 to 2 of 2x squared would be 4x squared, and then minus an x squared squared gives us x to the 4th dx. So an antiderivative for this function is pi times 4/3 x cubed minus 1/5 x to the fifth. And we're evaluating from x equals 0 to x equals 2. So let's see what we have. We had a constant pi out in front. When we evaluate at x equals 2, we have 2 cubed, which is 8, times 4/3 would give us 32 thirds, minus 2 to the fifth, which is 32, times 1/5 gives us 32 fifths. And then we subtract what we get when we evaluate at x equals 0, which is 0. So let's see what we're left with. I can factor out a 32 from each term in the parentheses, so I have a 32 pi, and I'm left within 1/3 minus 1/5. Now 1/3 minus 1/5 would be, let's see, 5 minus 3 or 2 over 15. And then taking that 2 over 15 times my 32 pi, I have 64 pi over 15. All right. So we see here or we start to see in this example why it is so helpful to sketch our region that we're going to revolve about a given axis, because it helps us to visualize what method we're going to use, the disk method or the washer method. And we can see here that our figure also helps us to determine what the outer radius or the inner radius of our washer might be. So let's look at some other examples. In this next one, we're asked for the volume of the solid obtained by revolving the region bounded by y equals x squared and y equals the square root of x about the x-axis. So again, in order to sketch our region, it might first be helpful to determine the points of intersection of these two curves. And in order to do that, I'm going to set these two functions equal to one another. That is, x squared will equal to the square root of x. So squaring both sides, I have x to the fourth is equal to x, or moving all variables to the left-hand side of the equation, I have x to the fourth minus x is 0. So factoring out an x, I have x cubed minus 1 is 0. So either x is equal to 0, or x cubed minus 1 is equal to 0, in which case x is 1. So let's sketch our curves. So we found the x-coordinates for the points of intersection were at 0 and 1. Now let's find the y-coordinates for these points of intersection. So when x is 0, y, which is x squared, or square root of x, would also be 0. And when x is 1, y, which would be 1 squared, or the square root of 1, is also 1. Now the graph of y equals x squared is a parabola opening upward, passing through 0, 0, and 1, 1. And y equals the square root of x, or x equals y squared, is a parabola opening along the positive x-axis, also passing through those 2 points. So my region of interest is this shaded region between those two curves. So if we were to revolve that region about the x-axis, we want to find the volume of the resulting solid. So let's think about taking a small slice through this region at a point x, somewhere between 0 and 1, of a thin width dx. So we can see by revolving that slice about the x-axis, we would have a washer shape So not a disk, but sort of a disk with a hole through the middle, which is a washer. So we know that we're going to make use of the washer method. So I'll say using washers, the volume of our solid is found by taking pi times the integral along the x-axis from 0 to 1. So we saw here the left edge of our solid was determined by x equals 0, the right edge by x equals 1. And the function that we're integrating would be the outer radius of our washer, which is the distance from the x-axis to the upper curve, which was y equals square root of x. So we take that outer radius of our washer squared, and then we subtract the inner radius, which would be the distance from the x-axis to the lower curve, which was our parabola, y equals x squared. And we're squaring that radius and multiplying by the small width of this washer-shaped cross-section dx. So integrating this, we're adding up all of the volumes of these little washer-shaped cross-sections from x equals 0 to 1, and that gives us our total volume. So simplifying here, we have pi times the integral from 0 to 1 of the square root of x squared, which is x, minus x squared squared, or x to the fourth, dx. Then the antiderivative of this function would be pi times 1/2 x squared minus 1/5 x to the fifth, which is being evaluated from 0 to 1. So we have pi times, when we evaluate at x equals 1, a 1/2 minus 1/5, and then we subtract what we get when we evaluate at x equals 0, which is 0. So finally, we have pi times 1/2 minus 1/5, getting a common denominator of 10, would give us 5 minus 2, or 3/10. So altogether, 3 times pi over 10. Cubic units would be, or units cubed, would be the volume of the solid being described here. Now let's look at a couple of other examples. So similar to what we saw for the disk method, when we're revolving some region about a line, well, the line that we're revolving around doesn't always have to be either the x or the y axis. It could be any vertical or horizontal line. So let's look at some examples using the washer method where our axis of revolution is not either the x or the y axis. So in this next problem, we're asked to find the volume of the solid obtained by revolving the region bounded by the curves y equals x squared and y equals x about the line y equals 2. So again, we might first want to sketch our region. And since this is a region bounded by two curves, it would be helpful to first find their points of intersection. So here we would set the two functions equal to one another. That is, x squared is equal to x. And so x squared minus x is 0. Or factoring out an x, we have x times x minus 1 is 0. And it follows that x is either 0 or 1. So let's sketch our region. So when x was equal to 0, y, which is x squared, or x, is also 0. And when x is equal to 1, y, which is x squared, or x, is also equal to 1. So our curves will pass through these 2 points. Now the first curve, y equals x squared, is again the parabola opening upward, passing through those 2 points, and y equals x is the straight line passing through those 2 points. That is the line of slope 1 through the origin. So here our bottom curve is x squared, top curve is y equals x, which are bounding this region between 0 and 1. And we're told here that we want to revolve this region about the line y equals 2. So let's sketch it out here. Let me give myself a little more room so I can draw this close to scale. So here we had y equals 1 and then y equals 2. So the horizontal line, y equals 2, is the line that I want to revolve around. So let's think about how to do this. So if we think about taking our region of interest and slicing it up into little vertical slices taken at, say, some point x along the x-axis between 0 and 1 of a thin width dx, we can see that if we were to take that little slice and revolve about the line y equals 2, we would have a washer shape. A washer instead of a disk, since our region does not come into contact with our axis of revolution. So once we know we want to use the washer method, we can set up our integral for the volume as pi times the integral along the x-axis from x equals 0 up to x equals 1. And the function that we want to integrate is the outer radius of our washer squared minus the inner radius squared. So let's think about how to find that here. Now, the outer radius of our washer is found by moving from the center of our washer, which would be right around the axis of revolution, out to the outer edge of my region. So let's think about how to find that distance, which I've just indicated here. Now, I know the distance from the x-axis up to this lower curve is given by y equals x squared. So the vertical distance I've risen is x squared. And the distance from my axis of revolution all the way to the x-axis is 2 units. So to get this distance from the center to the outer radius, I could take the total distance, 2, from my line to the x-axis, and I would subtract the distance from the x-axis to that outer curve. So that is 2 minus x squared, and then I'm going to take the square of that outer radius. Now similarly, to get the inner radius, well, I'm looking for the distance traveled from the center of my washer, which would be the axis of revolution, down to the inner curve for my washer. And I know that the distance traveled from the x-axis up to that curve is given by y equals x. And again, the total distance from my axis of revolution to the x-axis is 2. So that distance that I'm after for the inner radius of my washer is found by taking 2 and subtracting x of the distance from my upper curve to the x-axis, and then I'm taking the square of that inner radius, all times the thin thickness of my slice, dx. So once I have this integral set up, I need to evaluate it. So let's start by expanding these square terms in the integral. So we've got here pi times the integral from 0 to 1 of, expanding this first term squared, we have 4 minus 4x squared plus x to the fourth. And we are subtracting, if I expand this second term, I would have 4 minus 4x plus x squared. So that leaves me with pi times the integral from 0 to 1 of, let's see what we're left with when we collect like terms. So here we have a 4 minus 4, which cancel one another. Then I had a negative, or I was subtracting a negative 4x, which gives me a positive 4x. I had an negative 4x squared, and then I was subtracting another x squared, which leaves me with negative 5x squared. And then the last term I had was this plus x to the fourth times my differential of x. So the antiderivative of this is then pi times 2x squared minus 5/3 x cubed plus 1/5 x to the fifth, and we're evaluating from 0 to 1. So substituting 1 in for x, we have pi times 2 minus 5/3 plus 1/5, and then we subtract what we get when we substitute x equals 0, which is 0. So let's see what we're left with. Here we have a pi times, now we need a common denominator, which it looks like 15 would work. So 2 is 30 over 15, minus 5/3 would be 25 over 15, and then plus 1/5 would be 3 over 15. So altogether, let's see, 30 minus 25 is 5, plus 3 would be 8 over 15, times pi gives us 8 pi over 15 for the volume of this solid. So we see it's a little bit trickier in the case that our axis of revolution is not the x-axis or perhaps the y-axis, but where we might have to revolve about some other horizontal line. It's a little trickier to find an expression for the outer radius or the inner radius of that washer. So for our last example, let's consider the following problem. We are asked for the volume of the solid obtained by revolving the region bounded by the square root of x, y equals 0, which is the x-axis, and the line x equals 1 about the line x equals 2. So let's see if we can visualize our region. So we know that we're looking at the region bounded by the curves y equals the square root of x and y equals 0, which is the x-axis. So we know they intersect at the origin. And the graph of y equals the square root of x is this parabola opening along the positive x-axis. So here y equals the square root of x. Now when we're looking at, and then our line y equals 0, or the x-axis is shown here, and then we have the line x equals 1. So here x equals 1 would give us a value of y, which is square root of 1, or 1. So we see that we're looking at this shaded region here. And we're told to revolve this region about the line x equals 2, which would be the vertical line passing through x equals 2. So we want to revolve about this line. Now, in order to make use of disks or washers, if I revolve some region about a vertical line, if I want my cross-section to have a disk or a washer shape, I need to slice up my region into little slices that are perpendicular to my axis of revolution. So here, I'm going to take a horizontal slice through this region at a value y between 0 and 1. And the thickness of this slice I'm going to call dy, a differential of y. Now I can see if I take that slice and I revolve that slice about this line, x equals 2, I would have a washer shape. So let's see if we can make use of washers here. So I'll say using washers, the volume of the solid I'm interested in would be pi times the integral. In this case, we're integrating with respect to y, since we were using little horizontal slices. And I see that the boundary of my region goes from y equals 0 up to y equals 1. So here we're going to integrate from 0 to 1. And the function that I want to integrate is the outer radius of my washer squared minus the inner radius of that washer squared. So let's think about the outer radius. The outer radius is going to be the distance from the center of my washer, which is at the axis of revolution, out to the outer edge of my region, defined by this curve, y equals the square root of x. But the horizontal distance that I traveled from the y-axis to this curve is given by x. And this curve, which is used to define the outer edge, was y equals the square root of x, or solving for x, we have y squared. So this distance that I'm traveling from the y-axis out to my curve is x, which is defined as y squared. And the total distance from my axis of revolution to the y-axis is 2 units. Since we were at, since our axis of revolution was x equals 2. So the distance that I'm interested in from the axis to the outer edge of this curve would be the difference in those values. That is 2 minus the equation for the curve, which was y squared, and we're taking the square of that radius. And then we are subtracting the inner radius for our washer squared. Now the inner radius would be the distance from my axis of revolution to the inner edge of my region, which is this vertical line at x equals 1. So the distance from the line x equals 1 to x equals 2 is simply 1 unit. So that inner radius is a constant 1, which is being squared, and we're multiplying by that thin width of our slice dy. So let's see what we get here. Once we have this set up, we're ready to integrate, so we need to expand. And we have pi times the integral from 0 to 1 of 2 minus y squared squared would give us 4 minus 4y squared plus y to the 4th minus 1 squared is 1 dy. And so we have pi times the integral from 0 to 1 of our 4 minus 1 leaves us 3 minus 4y squared plus y to the 4th dy. And so now we're ready to find our antiderivative. which is pi times 3y minus 4/3 y cubed plus 1/5 y to the 5th. And this is being evaluated on the interval from 0 to 1. So evaluating at y equals 1, we have pi times 3 minus 4/3 plus 1/5. And then we subtract what we get when we evaluate at y equals 0, which would be 0. So we have out in front a pi, and then to combine these terms, we would need a common denominator. It looks like, again, 15 would be a good choice. So 3 would be 45 over 15, minus 4/3 would be 20 over 15, and 1/5 is 3 over 15. So let's see, 45 minus 20 would be 25, plus 3 would be 28 times this pi over 15. So altogether 28 pi over 15. So we see in this section a few different techniques for determining volumes of solids by thinking about slicing them up into little cross sections, finding the expression for the volume of a small cross-section, and then adding up the volumes of all of those cross-sections using the definite integral. So the techniques that we've explored here were called the method of cross-sections, where our cross-section might have some arbitrary shape, maybe a square, rectangle, triangle, semicircle. For the disk method, our cross-sections were shaped like disks or circles. And then we had a washer method where our cross-sections were shaped like washers, where maybe part of our solid has a hole through the middle. So in the next section, we'll start talking about how to evaluate volumes of solids which could not be evaluated by using any of the methods that we've discussed in this section.